education, an affiliate professor of physics, and the director of the Center of Science and Math in Context, or COSMIC, at UMass Boston. He taught high school physics for 25 years and was a 6 to 12 science coordinator. He is the past president of the National Science Teachers Association. He helped write the National Science Education Standards of the National Research Council and has served on other NRC committees, resulting in the reports How People Learn, Tech Tally, America's Lab Report, and Exploring the Intersection of Science Education and 21st Century Skills. He also participated in the creation of the NAEP frameworks for 2009 to 2019, the College Board Science Standards for College Success, and the NRC Framework for Science Education. He's currently the chair of the Science Academic Advisory Committee of the College Board, and he's project director of the NSF-supported Active Physics Curriculum Project that is introducing physics instruction for the first time to all students and leading a similar effort with active chemistry. Without further ado, Arthur Eisenkraft.
Thank you, Lisa. It's wonderful to be here. I heard you had a wonderful first day yesterday. So I travel a lot. This was really easy for me. It was just a subway ride here this morning. But I have to tell you that last week I had to go out to Louisville to do a couple of workshops. And I sit on the plane, which I do often. I try to get some work done, maybe a little nap. And this person sits next to me and says, "You want to play a game?" And I said, "No." And they said, "It's a good game." And I said, "Really, I have some work to do." And a few minutes later, we're still on the car now. He said, "Let me tell you the rules of the game." And I think this is going to be a horrible play. And he said, here's how it works. I ask you a question. If you don't know the answer, you give me $10. Then you ask me a question. If I don't know the answer, I give you $10. And I said, "No, I'm not interested." And then the plane takes off, and I'm trying to get some work done. And about 15 minutes into the flight, he said, "I'll change the rules of the game." I said, "How?" And he said, "I ask you a question. If you don't know the answer, you give me $10. Then you ask me a question. If I don't know the answer, I'll give you $50. I said, "Okay." And he said, "Okay, I'll go first. What's the height of the Eiffel Tower?" So I reached in my pocket, I took out my wallet, I gave him $10. He said, "Now you ask me a question." I said, "Sure. What's both a mammal and a virus?" And he thought, and he said, "On this flight they have internet. Do you mind if I use the internet?" I said, "No, have a good time." And so for the next 45 minutes, I'm doing my work, and he's just there. And then finally he turns to me and he said, "Okay, give me $50. I said, "Great." He said, "So?" I said, "So what?" He said, "What's the answer?" I said, I reached my pocket, I gave him $10. Want to play again? Let me tell you another story, a little closer to home. I was teaching a class that had lots of special needs kids. And around 9 of them in this class of 23, there were 18 special needs. 4 kids didn't speak English and a couple of others. And then it came to our first test. And so I knew that 8 or 9 of them had to go to the resource room to take the test, it would be read to, they could have scribe, whatever kind of modifications they need. And so I gave them the test. I said, "Oh yeah, go down to that room and they'll help you with the test and then you'll bring it back." And at the end of the day, the resource room teachers came to me and said, "What are you doing?" I said, "I thought they're supposed to take it with you and then you tell them." And then you're supposed to put them in a sealed envelope. You put each test in a sealed envelope. The student brings it, we break the seal, then we administer the test, we put it back in the sealed envelope, then we return. I said, "Why?" They said, "What if the kids should talk to one another on the way down to the test?" And I said, "Wait, between my room and your room is 5 minutes. If they can get information that's valuable on this test in 5 minutes. It's 3 weeks of instruction. I'll give them the 5 minutes in class. What do you think I'm testing? What do you think I'm asking? And that's what I want to talk about today. Where is the knowledge we have lost in information? So we all know from our going to school that there was sometimes open book tests, sometimes closed book tests. And so what we wanted to do was we wanted to see, we know test questions change if we can make an open book test. Well, we also know that now in this room, I would venture to say that 75% of people have internet 24/7. I will also venture to say that within 10 years, everybody in America will have internet 24/7. That's how cheap it's getting. That's how accessible it's getting. So now I want us to think about, because this is the problem I'm trying to figure out, so what are our tests going to look like when they're open internet tests? What questions are we going to change? Which ones do we throw out? Which questions are no longer valuable because information is that cheap? Because students are going to be asking us, confronting us with, why do I have to learn this? I can Google it. And it's a good question. So here's what I think is part of the answer. These questions. What does it mean? How do we know? Why do we believe in science? And why should I care? Why should we care? And I hope that we can see how these questions also would impact math education, history education, English education. The promise is we can teach better, assess better, help students perform better if we do these questions not once a year, but all the time. So let's take a look at the first question. What does it mean? So here are a bunch of science facts that we've learned. Newton's second law, energy is conserved. From biology, we all remember mitochondria is the powerhouse of the cell. And water is a molecule. So the question is, what do these things mean? Well, actually, we're very good at that. On our tests, we know how to ask questions. What does F equal ma mean? What does it mean to say the Earth goes around the sun? What does it mean to say the atom has nucleus? Oh, the atom has nucleus. There's a little center, a nucleus, all the positive charge, all the most of the mass, and then there are electrons somewhere around it. That's the atom. We're good at that question. So in active chemistry, we do that question not for one concept, but for every single concept, every 3 days of instruction in chemistry. So we start saying to people, what chemistry does is it explains the macroscopic phenomena, like how that egg you have on your morning sandwich got scrambled. And then knowing that chemistry can tell us the egg got scrambled, something must have happened on the molecular level to allow that to happen. What is going on with the molecules? And then to explain, to bridge between the macro and the nanoscopic, the molecular level, we have to then create or use symbolic structures like math and graphs, Lewis dot diagrams or whatever. So here's an example of that. In Boyle's law, the macro is that we know if we apply pressure to a gas, it compresses. At the nanoscopic level, we say, can you draw and label a picture of what those atoms might look like, those molecules of gas might look like? And on the symbolic level, we say, well, here's a graph. Here's a symbolic way of representing that. Tell me about what happens between A and B. Write a mathematical equation for that. Now, of course, even the what does it mean question, which we're very good at, we have taxonomies which allow us to tell, well, you can answer the simple recall questions. What is the chemical symbol for calcium? That used to be a question on chemistry tests. Maybe it still is on some chemistry tests. Or you can ask, what are the products of HCl reaction with sodium hydroxide, or why is light required for photosynthesis? We want more comprehension questions. Too often our tests have been filled with simple recall questions. So let's continue with that conversation. I once had this conversation with a principal, elementary school principal, and she told me, you know, the students have to learn the order of the planets, you know, Mercury, Venus, Earth, Mars, Jupiter. I said, really? And she said, yes, this is something all students should know. I said, okay, you're the instructional leader, that's fine. But when you teach them that, please don't do it during science time. Because it has nothing whatsoever to do with science. She said, what do you mean? I said, it's not science. It's something else. I don't know what it is, but it's not science. It's what's left over after the science is done, what I call the artifacts of science. So Carl Sagan said, science is knowing much more than it's a body of knowledge. The science question is, how do you know that Venus is closer to the sun? What evidence do we have? What does it mean? Well, first of all, what does it mean to say that Venus is close to the sun? That's a science question. It means, oh, the sun is at the center and the planets go around. That's interesting. But then the real question, the science, is never the what does it mean. The science is that how do we know that Venus is closer to the sun? And how we know that happened last June, when Venus made a transit across the sun. People all over America looked at the sun during the day and you could see Venus cut across the sun. The only way you can see Venus cut across the sun is if Venus is between the Earth and the sun. That's science, that's logic, that's what we know, how we know it. So we get to the second question, how do we know? And here we have the same 6 items in science, and the question is, how do we know any of these things? How do we know energy is conserved? Certainly not by any heating experiments, since energy is never conserved with those. How do we know the atom has a nucleus? How do we know water is a polar molecule? Let's take a look at this, the third one. The Earth goes around the sun. I'd like to tell you that everybody in America knows the Earth goes around the sun. Actually, 80% of Americans know the Earth goes around the sun. 49% know it takes 1 year. This is, I'm sorry, it's an indictment of our work, that this is what it's like. But if I then say, how do you know the Earth goes around the sun? If I ask you how you know the Earth goes around the sun, all of a sudden the number plummets.